So now we're getting into techniques for finding the derivatives. So far, we're looking at finding the derivative. We've looked at the formal definition where it said, we looked at the limit as h approaches 0, the f of x plus h minus f of x all over h. And this was equal to the derivative of x, and we denoted that with an f, and I call it prime, f prime of x. Another way to say it. Okay, so this would give us the derivative of a function if it was differentiable. So let's just kind of look at a couple of things. What if we had a function f of x, and this was just equal to some constant k? If we were looking at the graph of a constant k, y equals k, that's just a horizontal line through k. So k could be above the x-axis, on the x-axis, it can be below the x-axis. I'm just putting it, in this case, above. So this is our line y equals k. So if we took the derivative of the function, so f prime of x, what would that give us? So anywhere on here, if we took the slope, so like we could say we have a point at 1k, we have a point at 2k. Y is always k, but x is changing. So our slope here, right, would be k minus k all over 2 minus 1, or 0 over 1, which is 0. So our slope is 0. So the derivative of a constant is always going to be 0. So that's a main point. Well, let's look at if we had maybe f of x equals just x. Well, if we graph that line, if I plug in 1 for x, I get 1. If I plug in 2 for x, I get 2. If I plug in 0 for x, I get 0. Negative 1, I get negative 1. So I have this line that looks like this. So without using the formal definition, we can see here that any value here, our slope is 1. Rise 1, go over 1. So here I can see that my derivative, f prime of x, this is equal to 1. We'll talk about that more in a minute. What about f of x equals x squared? So that one's a little different because our change, if I looked at the graph of this, this is a parabola, and the rate of change is not the same at every point. We actually just saw that the derivative of this looked like a line. And we just talked about, you know, this was a decreasing portion, so I know that the graph of the derivative is below the x-axis, where this was an increasing portion. But let's just look at this, and let's take using the formal definition. We have the limit as h goes to 0 of f of x plus h. So plug in x plus h, wherever you saw an x, you got x plus h. And that quantity then is squared. Minus f of x, so that's just minus x squared, all over h. So if we distributed this out, x plus h times x plus h, just for time's sake, I'm going to skip and just do x squared plus 2xh plus h squared minus x squared all over h. So things canceled out, x squared and negative x squared, those go away. Here we have an h in common in the numerator, and so we could factor one of those h's out and cancel it with the one in the denominator. And if we had done that, we're left with 2x plus h in the numerator. So when we plug in 0 whenever x is going, or h is going to 0, this was equal to 2x. Okay, so f of x was x squared. We just found that the derivative f prime of x, f of x equals x squared. We just found that the derivative of f of x is equal to 2x. Don't think that let's say that you did all your work on x cubed. If you did that, you would find that this was equal to 3x squared. I'm just going to say it. If you had done all that work for x to the 4th, you would have found this was f prime of x is 4x cubed. F of x was x to the 5th. You would have found that f prime of x is 5x to the 4th. So I don't know if you guys can see a pattern happening here. That 2 on x squared for the derivative is out front. This 3 here, the cube of our original function, is in front as our coefficient for our derivative. So all of these powers just came down in front when we took the derivative. What happened to our exponents though? So from an exponent of x squared, we got x to the 1st power. From an x cubed, we have an x squared. X to the 4th, we have an x cubed. X to the 5th, we have an x to the 4th. So notice that this decreases by 1. Right, so same thing, from an x cubed to an x squared, it also decreases by 1. So we should be able to, hopefully, maybe, come up with a formula. So if f of x is equal to x raised to some nth power, then f prime of x this should equal, well, remember from here, the squared, it came down front. The exponent just came down in front. So the nth power is going to come down front, x, and then it was decreasing by 1, this exponent. So to express that by decreasing by 1, our exponent here, n, has to come down by 1. So n minus 1. So this is actually our general power rule. So the power rule. So what it says again is that f of x is equal to x to the n, where n is a real number. Then f prime of x is equal to n x raised to the n minus 1 power. So this is where it's helpful if we could rewrite things so that our exponent is a real number. And so we can do some manipulation by using rules of exponents. And so this is probably a good place to bring in the rules of exponents. So we'll call exponents. Okay, so remember, if you have the same base, so b to the m times b to the nth power, what we did is we added our exponents. So this would be b to the n times b to the m plus n power. So example, x squared times x cubed. This is x to the 2 plus 3 power, or x to the 5th. So power to power. So if I had b to the m power, and then this was all raised to the nth power, this is equal to power to power, you multiply the exponents. So b to the m times n power. For example, maybe x squared all raised to the 4th power. This would be x to the 2 times 4 power, or x to the 8th. Division, so same base. You had b to the m all divided by b to the n. It would be b to the m minus n power. So maybe x to the 5th all divided by x cubed. This would be x to the 5 minus 3 power, or x squared. Anything other than 0 raised to the 0 power is always 1. I have to put on that stipulation, b cannot be 0. So if I had 1 million all raised to the 0 power, it's just 1. And then if you you had maybe a to the m, b to the nth, and this was all raised to the t power. It's no addition or subtraction in between these variables. I couldn't do this if there was, but I'm going to use the same rule as before, and power to power is multiplication. So this is a to the m times t power and b to the n times t power. So for instance, x squared y to the 6 power to power, multiply. So this is x to the 2 times 3 power, y to the 6 times 3 power, or x to the 6, y to the 18. It's helpful if you have a negative exponent. Let's say you had 1, or how about, this is where we're going to use it more. If you have a base down here, 1 over b to the m, we're going to actually use it so that we can bring this up into the numerator and so that we could rewrite it. So this would be the same thing as b raised to the negative m power. So normally we did negative exponent, we could rewrite it by changing the position. If it was in the numerator, bring it down to the denominator to make it positive. So for example, if I had 1 over x to the 5th, this is the same thing as x raised to the negative 5th power. And then radicals, being able to rewrite from radicals to exponents. So let's say you had the nth root of x raised to the m power.
Professor?
Yes.
Before we go on to that one, can I ask you a question about the one above it?
Yes.
So if that was 5 over x to the 5th, would that then be x to the negative 5th over 5, or would it be 5x to the negative 5th?
The second one. So the question Joy was asking if this was 5 over x to the 5th, right?
Right.
To rewrite this, I'm only bringing up this x to the 5th piece. So the 5 is still in my numerator here. And to bring it up, but this would give me 5x, change the sign here. So this would be negative 5th power. So the 5 would stay in front. But let's go a step further. If this had been, let's say, 1 over 5x to the 5th, the 5 would have to stay in the denominator. And so we could think of this as 1/5 times 1 over x to the 5th, because when we're multiplying fractions, you multiply across on the numerator denominator. So this is 1/5 times x to the negative 5th. You don't really need that dot there. Oops. Try that one more time. Oops, that's not what I wanted. Oh well. Let me just start over. So radical, the nth root of x raised to the m. This can be rewritten. The index of the radical is the number that's in the denominator. And the exponent of the variable underneath is the numerator of the fraction in our exponent. So the nth root of x to the m could be rewritten as x raised to the m over n power. The whole point of that was so that we can now take derivatives pretty easily. Actually, before we do that, let me give you a couple more rules. So rules for derivatives. And before I do that, let me just give you notation. So there's different notation, means the exact same thing, but you just need to be aware of it. So notation for the derivative of f of x. So we already saw one of them. And that was with that little prime, f prime of x. There's d dx of f of x. So it's a d over a dx, and then the f of x function. So this reads I don't know how to write that, d dx. x. Well, sometimes we don't write f of x, maybe we write y. So dy all over dx. Or, which I don't usually see this one, all meaning the same thing, capital D, little x, f of x. I would probably read this as derivative of x of f of x. All mean the same thing. So now there's another rule of derivatives. So let's say f of x is equal to some constant k times f of x to the nth power. Then this is equal to k times f of x. Actually, yeah. No, it's not. So if f of x is equal to, we already did that one, a constant at 0. If f of x is equal to x to the n for any real number n, then f prime of x, we already got that one. Let k be a real number. Okay, this is why. If g prime of x exists, k be a real number, and g prime exists, then the derivative of f of x equals k times g of x. Is the following. So f prime of x is equal to k times g prime of x. Okay, why is that helpful? Basically, if you had f of x, let's say, is equal to 3x to the 4th power, and we want to take the derivative of that. I'm not going to normally do this, but if g of x in our case was equal to x to the 4th, we know that the derivative of this by that general power rule was we bring our power down front. So that would be 4x, and we would subtract 1 from our exponent. So 4 minus 1 is 4x cubed. By this rule, f prime of x would equal 3 times g prime of x. Well, we just found what g prime of x was. So this would equal 3 times 4x cubed. So that is 4 times 3, so 12x cubed. So normally, I would just bring my power down front, multiply it by my coefficient in front of that variable, and subtract 1 from my exponent. So if f of x is equal to the square root of x, find f prime of x. So this is where it's really helpful that we write this as a power, the square root as a power. So f of x, if there's no index showed, you know that that's an index of 2. And so using that, we could rewrite this as x to the 1/2 power. So we're using the general power rule to take the derivative of this. So if g of x is x to the nth, the general power rule says bring your power down front and so x, and then subtract 1 from the power. So if we bring our power down front, we would have 1/2 x raised to the 1/2 minus 1. Okay, so this is where you're going to get good at getting a common denominator. So f prime of x is equal to 1/2 x to the, well, -1 could be rewritten as 2/2 with our LCD. So if I have 1/2 minus 2/2, so subtraction fractions, just subtract the numerator, keep the denominator the same. So we have 1 minus 2, that would be a -1. So f prime of x is equal to this I'm not sure if they wanted it like this, or they might want it in radical form. Let's first talk about the negative exponent. We could rewrite this by bringing the x to the negative 1/2 down to the denominator. So I'd have 1 all over 2x to the 1/2 x to the 1/2 power. And then this is equal to 1 over 2 square roots of x. So there's another rule that's going to help us, because maybe we have just more than one term when we're trying to find the derivative. So rule of sum or difference. So let's say if f of x is equal to u of x, and then either plus or minus some other function v of x. And you're given u prime of x and the derivative v prime of x exists. Then when you take the derivative of f of x, you can just take the derivative of each piece. So take the derivative of the first function plus or minus the derivative of the second function. Unfortunately, this is not going to be the case when we're dividing or multiplying. Let's just start really easy. So if you have y equals 5x to the 4th plus 9x cubed plus 12x squared plus 7x minus 1. Find dy dx. So taking the derivative, so we have 5, we can use our general power rule, bring our power down front. So 4x to the 4 minus 1 power. Plus 9, bring our power down, which is 3, and subtract 1 from our power, so we have x cubed minus 1. Plus 12, bring our power down, which is the square, so 2x to the x to the 2 minus 1 power. Plus 7, bring our power down. So if the power is not there, right, isn't that just a 1? So we can bring the 1 down if you want to write 1, you don't really have to. So x to the 1 minus 1 power. And then the derivative of a constant, we said was 0. So minus 0. So we can clean it up a little bit. dy dx is equal to 20x cubed plus 27x squared plus 24x plus 7. And remember, x to the 0 power is just 1. So this is 7 times 1, which is just 7. Okay, so we found the derivative of y with respect to x. So I didn't get into much manipulation yet of rewriting terms so that we can use this general power rule, but there's a lot of times that we can do manipulation, and I started giving you those tools to do that manipulation with the power rules, the general, for the rules of exponents, or rewriting radicals in terms of exponents, or moving a variable up into the numerator so that the exponent, we can use that power rule. So I'm going to stop there because we're pretty much out of time. But we'll go over more examples on Wednesday.